Hey everyone, and welcome to this explainer. I'm absolutely thrilled you're here today because we're going to unpack the hidden logistics that make our entire digital lives possible. We are getting right under the hood to see exactly how the internet perfectly manages massive, mind-boggling amounts of simultaneous data deliveries.
Think about what your computer is doing literally right now. You might be streaming this explainer, downloading a software update in the background, and keeping, a dozen web tabs open. So, how does your computer do all of that at the exact same time without completely mixing up the data? Well, to understand this, we kind of need to reframe how we look at your computer network. It's not some magical black box. It's actually an incredibly fast, highly organized mailroom.
So, here is our roadmap for today. 1. Network bridges and ports. 2. Speed versus reliability. 3. Inside the UDP header. 4. Ensuring accurate delivery. And 5. Protocols in action. Let's start with Section 1, Network Bridges and Ports. Right here is exactly where the magic happens. The transport layer sits directly between your network layer, which handles the IP addresses, and your application layer, which is the actual software you're using. When a package of data arrives at your machine, the IP header uses a specific prot field to direct traffic. It acts a lot like a traffic cop. If that field reads 6, it directs the package over to TCP. If it reads 17, it shoots it right over to UDP. Now, the core of our mailroom analogy really lies in this routing block. If the IP address is what gets the data to the correct physical building, the port number ensures it actually goes to the correct specific desk extension. If you want to browse the web, your data is sent to port 80. If you're doing a file transfer, it gets routed to port 21. This incredible time-sharing transmission is exactly how your computer handles so many multiple tasks at once. And just to give you a real sense of the sheer scale of this system, 65,535, that is the massive number of distinct extensions or ports available on a single machine at any given second. But they aren't just thrown together randomly. As this spectrum illustrates, the ports are highly organized. Port 0 through 255 are strictly reserved, well-known ports for core services. We're talking things like port 53 for DNS or port 25 for email. Everything above that, stretching all the way up into the tens of thousands, is dynamically assigned for your standard, everyday user traffic.
Which brings us to Section 2, Speed versus Reliability.
So this is the ultimate network battle. It all comes down to choosing the right delivery courier for the exact job you need done. We've got two main heavyweights to contrast here. On the left, we have TCP, the Transmission Control Protocol. Think of TCP as your highly reliable, signature-requiring courier. It's connection-oriented and absolutely guarantees your data arrives perfectly in sequence. But of course, that takes time. On the right, we have UDP, the User Datagram Protocol. UDP is your blazing fast, instant delivery courier. It is totally connectionless and, honestly, absolutely does not care if your package actually arrived. It's built purely for raw speed. You can literally see the difference in behavior and action here. Look at TCP on the left. Before it sends a single byte of actual data, it performs this careful handshake. It literally reaches out and asks, "Hey, are you ready?" and waits to hear, "Yes, I am ready." Only then does the data flow. Now look at UDP on the right. There is absolutely no handshake. It just continuously floods the receiver with datagrams without ever stopping to check if they even reach their destination. Let's dive deeper into Section 3, inside the UDP header. We're going to look right inside UDP's backpack to see exactly why it is so incredibly fast. Notice the elegant simplicity here. Its header is a remarkably small 64-bit structure. That's just 8 bytes total. It doesn't waste any space with complex options. It only bothers to carry 4 core pieces of 16-bit info: the source port, the destination port, a length value, and a checksum. That's the whole shebang. Then it gets straight to the payload data. Pay special attention to that length field, though. It records the total size of the UDP header plus the data. But what's really fascinating is its absolute minimum boundary condition. Because the header itself is always 8 bytes, if the length field simply reads 8, it means we have this wild extreme scenario where the packet is entirely header with 0 actual data inside. It is literally an empty envelope flying across the internet.
All right, moving to Section 4, ensuring accurate delivery.
So here is a major complication. If UDP is so incredibly fast and, well, careless, how does the system ensure the package didn't just get dropped at the completely wrong IP address entirely? To solve this, network engineers came up with a genuinely ingenious concept, the pseudo header. As you can see, a pseudo-header doesn't physically exist in the transmitted packet. It's totally virtual. It's essentially hallucinated by the computer for a brief moment simply to run some absolutely crucial safety math. Here is exactly what that looks like. Because normal UDP doesn't actually know about IP addresses, this clever cross-layer trick essentially borrows vital data from layer 3. It pulls the source IP, the destination IP, and the protocol ID, which is 17 for UDP, into a 32-bit block. It deliberately breaks the strict boundaries of the network layers, just to act as a secondary safety net. Once it has that pseudo-header, imagine dropping it into a giant checksum generation funnel. The system drops in the virtual pseudo-header, the real UDP header, and the data payload. It takes all of that, chunks it up, and churns it through the ones complement algorithm. What spits out the bottom is a completely unique checksum value that perfectly, mathematically represents that exact delivery route and data. And here is how all of that math manifests in reality. This is an X-ray view of a real-world UDP packet querying a domain name server. You can clearly see the target is destination port 53. The total length is 42 octets, or bytes, and right down there at the bottom, there is that calculated hex checksum. That tiny string of characters is the ultimate mathematical proof that the data arrived exactly where it was supposed to go.
Finally, Section 5, Protocols in Action.
Now that we've seen the byte-level architecture, let's zoom all the way back out. Imagine you sit down to stream a movie tonight. Walk through this exact sequence with me. Step 1. Your computer needs to find the server quickly, so it uses the lightning-fast UDP courier to query the DNS. Step 2. Once it finds it, you need to log in securely. Your computer instantly switches over to the meticulous TCP courier to ensure your password is sent with guaranteed precision. Step 3. The movie starts playing. Your computer flips right back to UDP to handle the massive, continuous, high-volume video data stream.
To sum it all up, we are seeing the full stack in action here. The core takeaway from our explainer today is that network engineering isn't about one protocol being universally better than another. No way. It is about precision engineering. It's about perfectly matching the courier to the specific demands of the real-world application, flawlessly balancing reliability and speed based on exactly what you need in that exact millisecond. I want to leave you with a bit of a puzzle, a provocative final thought before we go. If a high-definition video stream relies almost entirely on the unreliable UDP courier, a courier we literally just saw drops packets without even checking, how does the software on your screen handle those missing pieces without just completely breaking the movie? Think about what the application layer software must be doing behind the scenes to smooth over those inevitable gaps. Thank you so much for joining me on this deep dive into the transport layer, and I'll catch you in the next explainer.